I thought I would take you, last time I was here was a long time ago. I talked about the high lava plains where I've spent a lot of time and a lot of my students have spent a lot of time. And, high lava plains is a really interesting place. It is super bimodal. I recently compiled how bimodal is the high lava plains compared to other places. And it is like basalts and rhyolites, most of which are high silica rhyolites, and there is very little in between. There's some, but very little in between. This place in the Andes is quite the reverse. You will not find a basalt, nor will you find a high silica rhyolite. It's all dacites and andesites. Okay, so it's a compressional setting. It's really thick crust. Out here, it's an extensional crust setting, and really, thin crust, thick crust, so on. So it's the opposite extreme. And what interests me is just how do magmas develop in these different tectonic settings over prolonged periods of time? Like how much heat are we delivering and how much are we changing the crust when we invade magma into it, which plays out in how do we make ore deposits, or it plays out in how do we grow continental crust, or how do we recycle things out of the bottom of the crust back into the mantle, and so on. But so I'm interested in the long time scale and what happens over a long period of time when you keep pumping magma in one place. I'm taking you to Chile now. I found this field area, which I call the Aucanquilcha volcanic complex. And Aucanquilcha means the big springs in Aymara, which is a local language. And there are some big springs out here, but this is the Altiplano, and it is dry as a bone here. And the interesting thing is that because it hasn't rained there since basically the Miocene, the volcanoes remain constructional. They still, they haven't been completely carried away by glaciers and rivers and so on. So there is a little bit of snow, as you can see on there. That's what they call Bolivian winter. It comes in during what we would call summer. So I was doing some regional mapping for the Chilean Geological Survey while I was down there on a sabbatical. And I found this clump of volcanoes and going, wow, they all look young, but they're probably not all young. And what can that maybe tell us about understanding long-lived, strongly crustal magmatism? And this is a project that's gone on for over a decade. There's a bunch of students who have worked on it. And also faculty, Frank Kepley and Todd Feely, and then with financial assistance, of course, from NSF and from the Chilean Geological Survey. So this is a view from the neighboring volcano, Ollagüe, actually from an airplane flying past Ollagüe. And you can see the big complex in the middle, that's Aucanquilcha. I'm going to show this here. And that's a long ridge, and this one has fumaroles on top. It's just over 6,000 meters, so it's very slow going once you get up there. And around it is a cluster of basically all of these volcanoes. There's some more out in here, little one back there. So a whole bunch of volcanoes, and then sort of plains around that. So it's a really distinctive cluster. So what can we learn by looking at this thing over a long period of time? And so what we're looking at is this part here. This is my hand-drawn sketch of magmatism featured on from basaltic to silicic. It's intrusive equivalence there. And we are looking at things that here we have ignimbrites, we have stratovolcanoes, we have little domes, and we have the surface expression, but can we infer something about what's going on underneath? And what I will show you later is that this complex has an uncanny resemblance to the Tuolumne intrusive series that is exposed at Yosemite. And that I think that is a pretty close intrusive analog. And I'll show you my arguments for that and what that implies about how much magma is left in the ground versus how much magma comes out. So why care about this kind of thing? So it's really how long do these systems live? An individual volcano, an eruption or an eruption cycle might last years to decades to maybe even a century or two. Volcanoes themselves, maybe tens of thousands of years to 100,000 years, maybe 500,000 years, and then big complexes that might live much, much longer than that. And in order to grow substantial ore deposits, you typically need multiple cycles of hydrothermal alteration. And these longer lived systems are perfect for making porphyry copper deposits, of which there are many in northern Chile, and also shallow level gold. And of course, and this is just my comic interpretation of volcanic plutonic connections. Okay, so a little bit about South America. I don't know how much you know about it, but it is the continent to the south of us. Actually, it's weirdly quite a bit to the east of us too. Because if you fly to South America, you actually go through Miami and you keep going east. So you go from the Pacific to the Atlantic back to the Pacific. It is a very peculiar experience. It's a classical, the andesite is named for the Andes because there's lots of it. And the volcanism here, where the subduction zone is divided into 4, if you like, active segments where separated by places where there's either ridges or aseismic ridges or the Chilean rise subducting, so the volcanism has been suppressed, but 3 to 4 active zones. And the central volcanic zone, I should do it on this screen so Zoom people can see it. The central volcanic zone is on the edge of the Brazilian craton out here. So it's on very thick crust, thick old crust. And it's quite distinct from the southern volcanic zone where things are it's a much thinner crust, and you get a lot of basalts associated with the andesites. Up in this country, you get some basaltic andesites, but no good basalts, and lots of andesites and daceites.
We can't see your pointer.
You can't see it, and then okay, so there's 2 screens here, so the Zoom people are not going to see my pointer.
Zoom sees this one too.
Oh, okay, great. I'm sorry. Glad you pointed that out. Well, here's the central volcanic zone that I was talking about, southern volcanic zone, and so on. Okay, so if we look at this little area here, this is the Aucanquilcha volcanic cluster, and in red are shown the active volcanoes on that piece of the arc. So you can see all those little blue ones are inactive, and some of them are quite old, it turns out, even though they look very young just to the eye. To the uneducated eye, as it were. You get re-educated about how much erosion is there. And really, this area it's almost like being on another planet. It's developed a regolith more than anything else, like just sort of weathering in place. And then shown here are 3 big copper deposits associated with plutons that I think are the equivalent of what we're seeing in the arc now, but the arc has moved to the east because of the erosion along the forearc. Let us turn then to looking at this area, still a regional perspective. Oh, first pictures. Right, so this is a big salar here. So this is the area where it's really, really dry. Any water that gets out into the basins evaporates. And there are some briny areas where there are flamingos and whatnot. And this is being heavily mined for lithium, both the brines and the salars proper these days. And then this is the Volcan Miño, which is about 2 million years old, but you can see it looks really, really young. And here's an old abandoned a sulfur mining town. And I'll talk a little bit more about that in a minute. And these are the Sernajemin, the Chilean survey guys who were our driver and cookers and helpers and whatnot. There were 2 guys helping us out. And then here, I'm showing some of the sulfur deposits. And these sulfur deposits were mined mainly by Bolivian miners because they can operate at a high altitude. So this is all 5,000 to 6,000 meters. And the sulfur was used in the early days at Chuquicamata and the other copper mines, mainly Chuquicamata, for smelting, to lower the melting temperature so that you can smelt the ore. They do it now by electroplating, and they don't mine the the sulfur anymore, but because of the sulfur mining, there are little abandoned roads all over this countryside. And once I huffed and puffed my way up to the top of Aucanquilcha, only to find that somebody had ridden their bicycle up there. There were bicycle tracks, so I don't know. Tougher than I is all I have to say to that. Okay, so Aucanquilcha, the volcanic complex, is shown here on the arc, and it is at the northwestern edge of a big thing called the Altiplano Puna volcanic complex, which is a bunch of calderas ranging in age from about 10 million to recent, and overlies a region that is, well, first of all, it's very thick crust. You can see here the contour. This is 70-kilometer thick crust. The contours you see is the subduction zone underneath. And this area here is underlain by a low velocity zone in the upper crust. Where upper crust here is, you know, upper to middle crust in normal places because it's so thick. So here's a cross section done by a German group showing this low velocity zone over a high conductivity zone underneath the Aucanquilcha volcanic complex and the whole Altiplano Puna region there. And it is thought to be anywhere from a few percent to maybe as much as 10% melt. So, and that's a very hard thing to figure out because it's all in how you model the thermal, the attenuation, whether it's thermal or because there's liquid there. But suffice it to say, it's a big squishy zone, and it's probably the closest thing we have to a living batholith today. And it has all kinds of interesting attributes, how deep it is and the density. And an interesting and important thing in a different version of this talk is that the lower crust here is very dense. So whatever is driving all this volcanism is leaving a very dense footprint in the deep crust, and you can hardly tell it from the mantle. So if people think about mantle peeling off and mantle rebound, crustal rebound and that sort of thing, this is an interesting area to think about that.
I noticed that grade angle of the slab, is that intentional or?
That's what it looks like. It steepens, yeah. It's shallow at first and then it dives down.
Why is it so thick there? You have two continental crusts overriding each other, or I think it just got smushed together?
What you're seeing there is the downgoing crust is just the black. And in the upper plate, that whole 60 kilometers, 70 kilometers is crust. So it's a thin crust going down, and then lower is the lithospheric boundary. So that's the slab. Did that answer the question? Okay. Okay, so this is a really interesting area, and even aliens think so. Aucanquilcha is there, the blue arrow, and there was, I believe this was in 2010 that an object came soaring in and was photographed from the nearby copper mine and by the military, and they whatever, it's a UFO. They are obviously here because of long-lived magnetism. So this is the part of the crew here. My student Barry Walker was on this last trip. I'd been there several times before, and he is a big, tall, colorful fellow. And he has got his arm around our cook, Lucho, and Frank Tepley, who is on the faculty at Oregon State, runs the electron microprobe and teaches volcanology and igneous petrology. He is here surveying our water supply, which is looking grim, but our mattresses are in excellent condition. Okay, so I want to go through this. This is the transect of here's Aucanquilcha itself, the active young volcano in the middle. And then these are all these others, and it's taken from one of the volcanoes on the margin. And there's our truck for scale. And so I want to make a couple of points. That there's a spatial development, that magnetism went from the margins inward, that there's compositional and mineralogical changes that go with that spatial change, and that there's a volume evolution where it's sort of puttering along and then suddenly goes into a big burst of activity. And we can document this here, and it turns out it has a lot of interesting parallels in other systems. So here's a simplified geological map with the oldest rocks are these here in red, which we call the Aucanquilcha group, named for one of the volcanoes in that group, this one here. And these are 11 to 6 million years old. So we did sampling, trying to get the oldest and the youngest. It's hard to get the oldest of these rocks because the volcanoes are still constructional, right? So inside their guts, there are probably older rocks, but we did what we could in terms of the exposure. And so that's the 11 to 6 million year group. Then there's the Gordo group, these tan ones that came next. They run from 6 to 4 million. And then there is this big outpouring after a pause of a couple million years. There's this big outpouring of the green, which we call the Polan group. And that's from 4 to 2 million years. And then Aucanquilcha proper, which is 2 to 0. Okay, so you get the idea. It goes from the edges to a big burst to the cherry on top. And here's how it changes in composition for the different times. So here's the oldest group, and it ranges from 55 to 68% silica. And it has different, the mineral assemblage is mostly pyroxene plus minus olivine, no hydrous phases to speak of. And pretty, it crudely bimodal. You don't know if you fully sampled it, but it looks a little bit bimodal. There's mostly these things and mostly those things and not much in between. Then we go to the next cycle here, the 6 to 4, the Gordo group, and you can see that the composition is collapsing a little bit. We're not getting decompositional extremes. It's filling in more in the middle. So andesites and dacites. And we're starting to get, we have pyroxenes as a dominant mafic phase, some olivine, but we're getting a little sniff of amphibole. So a litthere bit of water.
Is that due to mixing of the magma in the magma chamber, or is there any,
Why the amphibole?
how it goes from bimodal to
Yes, it is probably mixing. How it goes from bimodal to fully homogenized. Yes, there's a hybridization that's full sort of crustal gobbling up by the extant magma. Yeah. So then this we saw. So I'm just repeating it so you see it, can compare it. The next, there's just Pabellon. I've broken it out because it's an interesting transition between the 4 million year group and then the big flare up group, which is that it has a similar range in composition, but you can see that all the mafic compositions here are mainly featured as inclusions. So they're not actually free lavas, but they're actually little magmatic inclusions inside of lavas that are more silicic. So what that's indicating, I think, is this business of mixing, that you've now mixed up a low density magma stew, and the basalts or mafic things that are coming in at the bottom are getting entrained in little bits, but they're no longer making it through this low density cap. Okay, so the system is being thermally fed, but it's the material, mafic material, is only getting in as these little inclusions. Okay, and then we had that Pabellon cycle. Now we go to the flare-up cycle. So there we have, you can see that we still have inclusions down here, but the composition has moved strongly into the dacite range, right? And there's hardly anything, there's virtually no lavas left down here at this end. And then we go to Aucanquilcha. Oh, and add to that, we now have pyroxene, hornblende, and abundant biotite. So this is getting more hydrous. And then Volcanism, also a little outlier on the side, has its own history. It is a lovely straight up andesite volcano with a few little outliers. It's on the edge of the system, so it's not feeling that, maybe that density barrier quite as much. And then moving on to the last stage, Aucanquilcha proper, you can see it's moved over in silica even more. Our peak was here at 63 or so, and now we're moving over to a peak more like 65. Lots of biotite, 2 amphiboles, and it is the last thing. I mean, it's still active, so it's not dead yet. We don't know what's next, but I'd say this system is dying based on comparison to other systems. Okay, so you get the idea. Regional to central, diverse to uniform, and anhydrous to hydrous. Okay, so this is then the cumulative volume erupted in time. So showing how in the early stages it's diverse. We have a little bit of pyroxene hornblende, and then at about somewhere in the between 6 and 4, we develop a big burst of this hornblende biotite dacite that is the dominant volume there. So we have sort of after about half of its incubation time, we really cook this pot up of pretty homogeneous, pretty silicic stuff. All right, so let's compare that to other places. So here are a couple of other examples, and I put on here, so this is from 11 to 0. So this is from 40 to 34, so similar 10 million year time scale. This is from 15 to 9, so not quite as long. This is East Central Nevada, where I've done some work. A similar story where, and at Yanacocha in Peru, similar, you have early sort of more diversity in the mafic materials, and then after some period of time, some millions of years, you get a big stew pot of hornblende biotite dacite. And associated with these at Aucanquilcha, this is when we get hydrothermal alteration, such as we know it and can date it. At East Central Nevada, this is the time when we get big calderas. And in Yanacocha, this is the time that you get lots of gold mineralization and calderas. If you do the Rocky Mountain volcanic field, it tells you exactly the same story, and all the big calderas are at the growth of this big hornblende biotite dacite hump. So this is this long-lived pattern is a pretty common one if we look at things at the right scale. If we don't look at just the one volcano, but we look at a whole suite of things. All right, so next, a little break. This is Volcan San Pedro and San Pablo, which are active nearby. The next set of active volcanoes to the south, and here are some of these brines with lots of flamingos. And there's a couple of ecological tragedies that are worth mentioning that have weirdly something to do with people. Who knew? And that is in mining all the lithium brines and whatnot. This is, of course, where the flamingos live. And so they are becoming less common as their food source gets used up for lithium. And so, you know, there's a cost to quote green energy too that we need to keep in mind. And then a happy story, ecological happy story, is Volcano Yagüe in the background, and you can see in the foreground all these green hummocks, and then here's a close-up of these green hummocks, and you can sort of, there's a little flowery bit on there, but you can also see there's these little dots. Those are resin that ponds on the top of these they're very hard, they look like moss or something, but they're not at all soft. And they have the same energy delivery as coal. These are called yareta, and they were in the early days of smelting copper. They mined the dickens out of these things all over the place, and were smelting copper using this yareta. But since they've gone to electroplating, the yareta has come back really well, so it's looking good. Okay, so I want to get a little bit into nitty gritty here because it'll be interesting to compare it then to the history of the batholithic part of the story. And so one of the things that we can look at is to try and divine what is going on underground is the minerals that come up in the magma, right? And then they get frozen in the lava at the surface. And those minerals carry history about where they lived. And the zircon minerals, of course, carry, because of the uranium in them, they give us a time, they give us a clock. They can also, the titanium in them can tell us about the temperature. And so what I have here, and they don't dissolve very readily unless they get quite warm. So they carry history. And what I have here is the from 11 to 0 timeline for andesites in the gray and the dacites here in the clear. And then these are zircons that were dated at different from rocks of an age that we knew from argon dating. And then you look at the youngest zircon age, usually the one nearest the rim, and they match well with the argon ages, but the zircons have pores that carry an older history. Well, in all the zircons we analyzed, there were only 2 that gave us Mesozoic ages, so they were clearly xenocrysts and trained. A few gave us some ages that are a little bit older than anything we see, but not very much older. And most of them just have little short tails. And you'll notice that, so these little short tails go out to about the age of the complex. And then everything beyond this sort of big burst, here it only goes out to the age of that burst. So you're kind of resetting the whole crustal story. So these are all zircons that are part of its history, and they're being recycled internally. They're not just picking up junk from the walls. And it's just, we'll see how this looks quite similar to things that we see in the Tuolumne series. And then just a little word about the amphiboles. The reason that I emphasize amphiboles is because amphibole has aluminum in it. And aluminum is one of the few elements that, can occupy the tetrahedral site substituting for silicon, or it can occupy an octahedral site substituting for magnesium or iron or whatever. And it will be a different diameter. So it's compressible because of its electronic structure. So the higher the pressure, the more likely it is to be small enough to fit into the silica site. And so you can get more aluminum into it at higher pressure. So it's a barometer. So we can tell where was that amphibole when it acquired its aluminum signature. So it's not a very precise barometer, but it is one. And you can also, the calcium aluminum exchange tells you something about the temperature. So you can use it for a thermometer and a barometer. They're not perfect, but we do what we can. Okay, so if we look at the time here for the Aucanquilcha group, going from the old ones here, sorry, I turned the axis on you. Old is on the left, young is on the right. Here's the Aucanquilcha group and on down to the Aucanquilcha group. And what we see here is that the amphiboles are giving us a history of pressure. Here's the pressure axis of basically shallow to mid-crustal pressures, whereas the pyroxenes look mostly to be entrained from an older history that was probably deeper and more mafic. Okay, so when these things erupt, they're basically reaming a whole crustal column, and not all of that magma is directly related. So Barry Walker wrote a very nice paper about that in 2013. And then we'll compare this pressure history from the amphiboles to the pressure history that we see in the Tuolumne series later. You also see that it's a more restricted pressure region right here during the big flare-up time, right? And it's more pressure variability early and late and less in the middle. This is also the hot time, and these times are cooler times on the 2 ends. So this is the temperature history against that, going from 12 to 0. This is our time of volume max in here, and these are different thermometers. And the red line shows sort of the average of the iron titanium oxide thermometer, which is probably the most reliable one. And it definitely shows that things are warming in the middle part of the cycle. The zircons are not terribly informative, and the amphiboles also mimic this warming during the high volume time. So this is the picture that we kind of get from looking at the rocks and looking at the minerals in the rocks, that there's an early stage in which we have diverse things coming from, we're not sure how far, but basaltic andesites evolving into, which is the brown, into andesites, which evolve into dacite with some crustal mixing, but maybe not that much, into that slightly bimodal early slate. That then becomes more dacitic, starts evolving some water. Then we start trapping things in a big reservoir and develop over it a big dacite reservoir that erupts that big time, that big volume hornblende biotite dacite. And then the system cools down and things can get back through this weird big giant mixed pod that we had. Okay, so this is the time where we only make inclusions in trap there. Everything mafic is trapped there except for Volcan Mino that stunk out on the side. Got the picture? Any questions about that?
Yes.
Good.
Is that slide generated from data, or is this an artistic conception?
This is strictly artistic, but it is built on data in that we know the depths and we know the time frame and we know the compositions. So the color tells you, I know the composition, the depth, I know it from amphibole, and the age, I know it from dating.
I have a question.
Yeah.
So those graphs you showed us earlier about where the bulbs are.
Yeah.
We're talking about the surface expression of the volcanic material in those graphs.
No, we're talking about the conditions in the magma system underlying it.
Okay.
So the thermal high was during these two time frames. That's when the amphiboles and the iron titanium oxides were feeling the highest temperatures.
And the green is the pyroxenes.
Yeah, it's mafic, mainly pyroxene bearing.
Okay.
And then did you say the last one, it cools down, so more stuff can get through?
So yeah, so this, things can't get through very readily here because they're trapped in this low density magma sea, if you like. So yeah, so we can start getting, there are a few little basaltic andesites that get here, not exactly in this frame, but yeah, it looks like the system is dying down. So that must leave a crystallized mass below, right? So now I want to talk about, what is this picture? Is this real? Like, what does this really look like? It turns out I know that. At least I think I know that. Okay, I don't know that, but here's an argument I will make. Okay, so here's the Aucanquilcha volcanic cluster up here that we have seen before. The surface expression living right here. And then we go to the Tuolumne intrusive complex. Here is sitting right in here. And there are other plutonic complexes spaced along there with a sort of 50-ish kilometer spacing. So, the next cluster we would expect it to be associated with this place. And maybe another cluster down that way if we looked at it that way. So that's something yet to be done. Okay, so what are the analogies here? They have an aerial footprint that's kind of similar. They are built on crust that's very thick. At the time of the making of the Sierra Nevada batholith, at least the Cretaceous part here that the Tuolumne is, there is good paleo river drainage evidence and other kinds of evidence, but that's the best one, that there was a very high and very eastward continental divide, and that we had a thing called the Nevado Plano, that Nevada was basically at the height of what the altiplano is today. So it was a very thick crust and high elevation. So they're formed in a continental setting on thick crust. They have a similar footprint here. The Tuolumne intrusive series is a little bit bigger footprint, but very similar timescales. They last about 10 million years. Okay, and then if you look at the map of the Tuolumne, these dark units, the Kuna crest and whatever these are all called, these are more mafic. These are diuritic. And as you get inside, this is, you know, the half dome granite diorite, and then you get the Cathedral Peak granite, and then you finally get the Johnson granite. And there's a little more Johnson granite up here they've now found. But you can see that it's concentric, and over the same period of time, it becomes, you know, more centralized. And the largest volume eruptions are these ones that what I would call equivalent to the biotite hornblende dacite, this half dome and Cathedral Peak units. So let's look at their little zircon stories. We went through the zircon story here at Aucanquilcha. If you do the same sort of mass in time and what are the tales of the little zircons telling you in the Tuolumne intrusive series, it turns out they too are mostly recycled from their own parts, and they too are part of this big, there's a, after whatever this is, 2/3 of the history of the Pluton, of the Plutonic complex, you get this big pulse of intermediate composition stuff. So incremental assembly, but systematic. And then looking at the pressure, the depth of the system, this is a compilation of the hornblende barometry that we did in time, and then superimposed on that is so that the yellow bar or orange, whatever the color is, that's orange sherbet versus this big orange box, which is the full pressure range, but the lower end is occupied by pyroxenes. And in some places we actually have two amphibole populations, a shallow one that crystallized up here and a deeper one that crystallized down there. So here there's 2, 2, 1, 1, and then back to 2. So this is the time of homogenization and lots of stirring. Thank you very much for bringing that up. So the amphiboles are not segregated, and the times that are a little bit cooler and we have separate stirring pots, we have 2 amphiboles. So central volcanic zone of the Andes in general, this is their amphibole profile. If we look at the Tuolumne intrusive series, the amphiboles look like this, and the pyroxenes plus amphiboles look like that. Northern Cascades, the whole APVC plutonic inference from the low seismic velocity would be this bar over here. Okay, so this is what we're looking at. That's a pluton, and these are the plutonic equivalents that we're seeing. So I think that the argument that this is that the Tuolumne works well as an analog is pretty strong. And then looking at this diagram, this is epsilon neodymium, so neodymium isotopes against strontium isotopes, age corrected. So we're looking at the signature of the magma at the time that it was made. What we have here is the Aucanquilcha group, and the next group, and the next group, and the next group. You can see here's the Aucanquilcha series doing this. And we look at the Tuolumne series, and it's doing that. So a very similar range. Basically, this trajectory is a crustal assimilation trajectory. A depleted mantle source would be something like 702 something up here, and around a positive something or other like there. So that would be mantle. And if we then contaminate it with a bunch of crust, which is easy to do when you have a big old fat crust, and here you go, you get this pattern. But look, it's a very, very similar range, but you can sort of see a little hint that this is not a swooping down curve, but a little arcing up curve, which I would argue is because what you've done is you've taken this pluton that had a little bit of melt in it and you've squeezed the melt out to make the volcanic rocks. And what you're left with is something that is a little bit enriched in plagioclase mostly. And that plagioclase carries a lot of strontium. So on a trajectory like this, it will look like something that contaminates readily with strontium. Okay, so it'll be sharper that way. So I think that it's basically the intrusive analog, if you like. So I hope I have made a somewhat compelling argument, and this is actually a paper I want to work with Val Nemetti, who's done a lot of work in the Tuolumne to see how close we can make these, understand how these things complement one another. But they have similar footprints. They have similar lifespan, incremental assembly. There's a big volume pulse after a certain time period. They have this crustal strontium neodymium isotopic evolution. And the magma residence is somewhere between 3 and 20 kilometers. So if we then look at the area, the erupted volume, here we have to go with inference just how deep. We can do some estimate of how many cubic kilometers are there of each of these things. And if they are analogs, that means the intrusive to extrusive ratio is about 50. There's about 50 times more stuff down there underneath the Aucanquilcha complex than ever got out. Stuff that looks like the Tuolumne intrusive series. And why is this a big deal? Well, it tells us a little bit about continental reshuffling, how you rebuild a continent, how you distill a continent. But modern estimates, if you look at Joanne Crisp and others, Crisp and Sparrow, excuse me, that typically you don't usually see numbers larger than 10. But in fact, it's at least 50. And if we even think about all the underplating underneath that made all that really dense lower crust, all the mafic things that have to be underneath there too, if that's the intrusive equivalent, is it not? So then maybe these ratios are more like 100 to 1. So I think it's an interesting thing to think about. And what that means is really only 2% of the magma is extracted. Most of it is left in the ground, right? And this might not be monstrously surprising, but I think it's good to have a real number in your mind for at least in this place where the crust is very thick. Okay, so we're looking at sequential sampling of a long-lived crustal magmatic system. I think this is exactly the kind of system that makes a porphyry copper deposit. And an interesting thing to do would be to look at the evolution of chlorine and chlorine and sulfur through the history of the system. And we could do that here. The proposal remains to be written, but there is actually anhydrite, magmatic anhydrite in some of these, so we can track sulfur evolution and sulfur isotopes. And of course, apatite hosts fluorine, chlorine, sulfur, and there's plenty of apatite in all of these things. So kind of tiny, but still. So there's interesting things about analogs to ore deposits that we can continue to think about. There's a waxing climax and waning system to this. So there's a life cycle here that we're tapping an evolving plutonic complex, much like the Tuolumne, and that the intrusive extrusive ratios are much larger than anybody has imagined. Oh, got one more thing. Did anybody having a birthday? Here's your birthday cake. They love colorful cakes in Chile.
And we'll take questions and be sure to repeat them.
I will do that.
Yeah, the Zoom people are gonna riot if you don't.
Riot! We won't see it, so what do we care?
Virtually.
A virtual riot.
I guess one thing was unclear to me, were the map units that you were describing extrusive rocks or intrusive rocks?
Extrusive rocks.
They were all
The one at Aucanquilcha?
The question, repeat.
Oh, sorry. Question was, the map of the Aucanquilcha complex, were those extrusive units or intrusive units? Those were extrusive units. It's all volcanic.
So both lavas and like ignimbrites, or was it primarily just lavas?
It's almost exclusively lavas. There is an ignimbrite that is the age of the time gap. But as far as I can tell, it does not come from there. It comes from further east. Yeah, and there are lots of other ignimbrites in the area, but no, this is a lava system. Not much explosive at all. Not much tephra. Of course, that could have blown away. Erosion is done by the wind here, and they use it as a Mars analog for a reason. Yeah, it can be rough. Very abrasive. Yeah. Exfoliation.
All right, so John asks, I'm curious, or how is the data of age, composition, and volume collected?
Right, so the data for age is collected by choosing a rock that you think is the youngest or the oldest or something representative of the volcano you're interested in, and then doing argon dating. So we did argon dating at Oregon State, and we did some zircon dating, which I showed the zircons, uranium lead for that. And then the volume, that's a really good question, because this is something that I don't want to fault any of my colleagues for doing this, but to get the volume of a volcano, it's easy when it's young, but it's hard when it's old. I mean, I worked on Goat Rocks, which is, up by Mount Adams, past Mount Adams. There's nothing left, and it's really young. It's been glaciated. But here, because they're constructional, we can take a stab at reconstructing the volume of the volcano at the time, back in time. So we have an unusually good volume record. And then the last question was composition. That you take the sample, and if you do major elements with some trace elements, we grind it up, send it to Washington State University to use their XRF. And some of them were done by laser ablation trace elements at Oregon State.
So you compare this system to that of the Sierra Nevada and
Yeah.
Yosemite area, and I'm assuming, because that system, was born and died a long time ago, and now the plutonic part of the system is being exhumed, that's why you're looking at, in your comparison, you're saying down under the ground, under these current volcanoes, it looks like that.
Yeah, I mean, I know from the history of my minerals and whatnot that there has to be something down there, right? And this is roughly the attributes that it has to be. It has to be able to be dacitic, it has to be able to have biotite and amphibole, and it has to be so and so deep and so on. And it has to live for 10 million years. And where in the world can I find a pluton that looks like that? And it turns out that Tuolumne is a really good match. I've looked at a number of systems, and partly it's one of the best studied plutonic complexes ever, so that makes it easy to compare. There are not that many places where people have done really careful work for a long time. It's just a lot of work to map a giant plutonic complex.
Can you point out the centralization pattern in the diagrams, like the artistic diagrams, if there were 4 diagrams?
Yep. These are trying to show to scale. This is where the volcanoes of that age erupted, and the next age, and then this age, and then the final age. It's a lot better in the map pattern. You want to see the map pattern? I want you to see the map pattern. Right. There's a ring. And of course, you don't know if that stuff is underneath too, right? I can't exclude that it is underneath too. And then there's this ring, and maybe there's some of that under here too. But there's definitely this crazy burst of green. And then there's this little top of the sundae here.
I can vision on that map. I can kind of identify like water, how it would flow and fill in each different section. But between each magma flow, I assume the core cools. And so when you're trying to envision the next flow that happens after that, is the flow flowing around the cool core, or is it remelting its way through the previous pluton?
And try to repeat the question.
I will. So the question is, When the magma flows on the surface and solidifies, is that right?
Well, I'm talking about, no, I'm talking about below,
Oh, below, when it comes up underneath,
yeah, is it remelting, is it melting its way?
is it melting its way through?
Right.
Probably not. It's buoyantly rising along cracks, probably.
Right.
So how does the magma rise, and how can successive batches of magma rise?
Yeah.
So I would argue that these guys were making an arc-like peripheral. There was probably a somewhat circular fracture, and these guys too. That the whole area was probably doming and uplifting and cracking, and then allowing those things to come out along those, almost like early stages of a caldera, but it never got explosive. And then these middle things, I can't really see a pattern. This one is a straight pattern. This one, maybe not much of a pattern. This one clearly is straight. So there are some kind of fractures that are helping to guide the magmas up from wherever they're formed at depth. Does that help?
Yeah, it does, it's just something I was trying to visualize.
Yeah, it's a great question. And, you know, in the end, the structural overprint does matter in terms of how stuff gets out of the ground.
Jason asks, any basement metamorphic or co-evolved gabbroic rocks exposed in the area?
Yes, not directly here on the arc, but as you go, the Altiplano drops off sharply to the sea, and there are deep canyons that expose, old metamorphic rocks and gabbroic things, but never anything you would say, oh, that's the plutonic equivalent. It's not far enough to the east. It's not under the arc, but you do see a fair bit of the basement. And those have been sampled for isotope characteristics, and there's all kinds of sort of continental domain maps made out of that.
Yeah, Denny,
Dan,
you know, one of the slides plotted some data about amphipoles.
right,
I just wondered if you could help me get
something more out of that slide. Oh, I'm sorry, I never even explained to you what this was.
Number 25.
25, this one.
What does that tell me?
Okay,
No, it's time.
And repeat the question.
yeah, I will repeat the question, thank you. Okay, so the question is, what about those amphipoles? Can you help me understand them? Is that right?
Yeah, I wondered what that is.
What is this telling us? Okay, so let me go back to this slide. So here is an amphibole right there. And here's another amphibole here and another little one here. Okay, so these amphiboles, you can take the electron microprobe and you can hit different spots on the amphibole and get different compositions, and that's what these little points are. And these are the points for the Aucanquilcha group. You can see there's 2 clumps of amphiboles, and the Aucanquilcha group, there's 1, 2, and the green and the 2 middle stages, it's all kind of messed together. Okay, so the aluminum in this amphibole gives me the barometer. And so you could plot on this axis here, aluminum content in the amphibole, and that correlates to pressure. Okay, so these are the amphiboles, the diamond shapes. And then aluminum barometry, empiric scenes is the boxes. And I've just shown in the red field here, just the amphiboles themselves, just to make the point that during the high volume, hotter, more homogeneous time, the amphiboles are coming from a more restricted pressure range. That's the argument for making that sort of very orange blob in the middle of that cycle.
Carrie asks, so all the Chilean extrusive hasn't eroded off due to dry climate. Does that mean that our Cascades, aside from the alpine glaciation, had considerably more volume at one time? And is there also huge volume at depth beneath the Cascades?
The answer to that is yes and yes, but I could flesh that out a little more, which is that for sure, a lot of mass has been lost through erosion. And because it's a wet climate and the glaciers took a lot away. So, so it's almost impossible to reconstruct the past volume of the early arc. In fact, it's impossible. That said, there are some, during John Day time, there are distal ignimbrites and things that you could probably make some cracks at getting at the volume. But yeah, it's really hard to do. We've done it a little bit for the Deschutes Basin because there a lot of the volume was ignimbrites that went out into the Deschutes Basin, and so they haven't been eroded away. But it's a hard number to get. But that said, there's a clever calculation that Till and Kent did, where they guesstimate and try to make erosional compensations for how much there was. And then they say to make an andesite, you need this much basalt and that much rhyolite. And if I mixed it, and I think there's this much, then I can estimate how much basalt had to have been added to the crust. So they make a crude estimate and try to correlate it to the seismic velocity of the lower crust. It's a really clever idea, and it probably works if you get better input, but they were having a real hard time reconstructing volumes.
Well, I was just wanting further clarification on this whole pyroxene amphibole thing. So you have magma coming up from, there's hot steam and magma coming up from the subducting crust, right? And it's creating a basalt magma chamber, and that's where these pyroxenes are developing.
Yep.
And then
We're going
as
here.
the magma goes further up in the column, it and mixes with more of the continental rocks. We have conditions that turn some of that pyroxene into amphibole.
That doesn't turn into amphibole. You just also get amphibole.
Okay.
Some of the pyroxenes are overgrown by amphibole, but mostly it's pyroxenes and amphiboles.
Okay.
Yeah. And so let's look at this time frame. So basaltic andesite, which started out somewhere further down as basalt and eventually worked its way up here to be basaltic andesite, is thermally feeding the system and going up into dikes and ponding at whatever density level is appropriate and is making whatever minerals are appropriate for that level and that composition. They're at this point, they're andesitic. That would be the green color. They've sucked up a little bit of crust and they've fractionated. You've left some pyroxene behind and some olivine behind and making a more differentiated thing. Okay, so we have these guys happening. Some of that goes up and makes little dacite chambers, and then maybe comes an eruption that comes through all of this, and it carries with it pyroxenes from below, amphiboles from the middle, and barksome up on top. And most of these eruptions are very mixed. They are tapping more than one magma level, and we see that at this age and this age, we have a lot of tapping of different things. And at this age, things are much more homogeneous. It looks like we're only tapping this area. And then here we tapping through a whole different set of columns again.
Personal question. So did you say that the explosive volcanism was at the end?
There is no explosive volcanism.
Oh, okay.
Yeah, essentially none. Yeah, we found a few little tepras, but and like I said, the wind would have carried a lot of it away, but it's really remarkable. This is an effusive file. No.
I see that you're differentiating by composition mostly, but how does texture play into that? And do we get different textures, like coarse grain versus, extrusive versus intrusive, or fine grain versus coarse grain?
Yeah, the andesitic rocks tend to be finer grained and the dacitic rocks tend to be coarser
So
grained.
that has to do with cooling history.
It has to do with cooling history, how long they've been sitting in a chamber, how much time they've had to grow. So I'd say that the dacite chambers hang out more. They're also more viscous, right? So
They don't cool.
They don't move as quickly, yeah. And I forgot to repeat that question. She asked whether or not there was a textural relationship, a fine grained versus coarse grained for the different lavas. And there is crudely a compositional one, yes.